Okay, in this video lesson, I'll be explaining the solutions to the equation of simple harmonic motion and then try to draw a graph or show the graphical representation of the variation of acceleration of simple harmonic motion with respect to time. Now, simple harmonic motion has been defined in terms of acceleration. That the acceleration of a body in simple harmonic motion is given by this minus omega squared multiplied by the displacement of the body. And in calculus, this acceleration can be written as the second derivative of the displacement with respect to time t, that is d squared x over the t squared. That is another expression for acceleration in calculus. That's also equal to minus omega squared x. Now, this very equation is called a second order differential equation. I can write it as, write it this way, the squared x over the t squared plus omega squared x. This is second order differential equation. Now, if I take d over dt as equal to d, use the uppercase letter d, then it means that the squaring both sides, I have the squared over the t squared will give me my d squared. Now, I can decide to substitute that in this equation so that I can have from here that d squared x plus omega squared x is equal to 0. Okay, I can include the 0 here, equal it to 0. So that this gives me the squared plus omega squared multiplied by x is equal to 0. Okay, so that once again, this gives the second order differential equation. This d squared is my operator. It is just my d squared over the t squared. And whenever this equation is solved, this second order differential equation, it gives rise to two solutions. Because the second order, the first order differential equation, when solved, always produces one solution. Now we are going to apply that concept here. Look at it in that perspective. That is the equation of simple harmonic motion. And sometimes in solving equations, whether differential equation or whatever equation, the conventional thing is for you to start from the problem and solve and get the solution. But it's also correct to start from the solution and solve from the solution until you arrive at the problem or the question. So that's what we're going to do. I'm going to show to you or prove to you that the solutions of this, equation of simple harmonic motion are x is equal to x naught sine omega t, where the x naught is the amplitude and omega is our angular frequency, and or x is equal to x naught cos omega t. So these are the two solutions, and we're going to show that these are the two solutions of this simple harmonic equation. So how do I do that? I want to start from the solution and solve back to the question, and solve back to the problem, and solve back to the equation of simple harmonic. Let me start with the first one. Now, of course, you should understand that the derivative of the displacement with respect to time gives velocity, because speed or velocity is change in displacement or dx over dt. So which means I'm going to differentiate this displacement equation with respect to time, and that will give me what? I'm sure you remember your displacement. Differentiation. If you differentiate sine, it gives you cosine. So this x naught is a constant, it's not differentiated. When I differentiate sine omega t with respect to t, now this omega will be moved to become a coefficient of the derivative of sine omega t. So that I move this here, then I differentiate this, that gives me cosine. Then I replace my omega t. So this is my dx dt. It gives me x naught omega cos omega t. And remember that the maximum velocity was given as omega multiplied by the amplitude of oscillation. If you recall that in my previous video, this is the expression for maximum velocity. So I'm going to replace that this v, which is instantaneous velocity, so to speak, of the body in simple harmonic motion, is equal to peak or maximum velocity cos omega t. All right. So we need to bear this in mind. Let's just keep this in one. Let's call that equation 1. Now, I can equally show that the variation of the velocity with time is a cosine graph, gives rise to a cosine graph, but the variation of displacement with time was a sine graph. Okay. Now to arrive at the acceleration, I have acceleration A is equal to change in velocity. When you differentiate velocity with respect to time, that gives you acceleration, meaning that I'm going to differentiate this velocity equation again, the one I called equation 1, and then denote it as equation 2. So differentiating velocity, I'm going to have my v naught, which is a constant, it remains a constant. Now this one must come this way to become a coefficient of the derivative of cos omega t. Then differentiating cosine gives you negative sine omega t. My negative can come in here. So that gives me negative omega v naught sine omega t. So this is my acceleration, okay, equals to minus omega and all that v naught sine omega t. Okay, so let me rewrite that here so that I can make it clearer. So this is omega v naught sine what? Omega times t. And recall that v naught was our maximum velocity and is given by omega times the amplitude of oscillation. So if I substitute or replace v naught with omega x naught, I have acceleration equals to minus omega squared x naught sine omega t. There's something I'm going to do here. Look at this term, x naught sine omega t. Come back to the starting point. We started with the displacement equation, which was x is equal to x naught sine omega t. So which means x naught sine omega t is my x, which is my displacement. Meaning that if I come in here now, I can replace my x naught sine omega t with x, with just the displacement x, so that this equation reduces to acceleration equals minus omega squared times x. So this gives back our equation. So we started with the solution and we have solved back to the question. And what was the question? The equation of acceleration of simple harmonic motion. And maybe I should give you as an assignment, this is your own assignment. Try with x is equal to x naught cos omega t, and then that's another solution of the equation of simple harmonic motion, and solve back to the equation of simple harmonic motion, which gives you minus omega squared x. All right, so that's an assignment. Now lastly, we want to see how these parameters, acceleration, velocity, and displacement, how do they vary with time? Okay, so let me start with the displacement graph, displacement time graph. Let me just quickly draw that here. Now I have here, maybe I can also draw for the velocity time and the acceleration time. Let me just include the three axis. So this is with respect to time, with respect to time, with respect to time. So this I'm trying to do here. So I'll call this my displacement. I want to mark the same point. Let me mark this point, this. Let me call this 90 degrees. I call this 180 degrees. This is 270, 360, and so on. So the same point. I take this down so that I can mark equal points on the three different axis. So this is my 90, my 90. On this is my velocity time, and this is my acceleration axis. Okay, so I have displacement time, velocity time, and acceleration time. Alright, so we are trying to see how these parameters vary with time. This is 180, 180. This is okay, let me draw this one quickly. So I have, this is 270, this is 270, and then quickly this gives me 360 and 360. Okay, so we have, I'm starting with this displacement. Remember that this displacement equation is a sine equation, called that a sinusoidal graph. So sinusoidal graph is drawn this way, 180 degrees, 0 at 180, negative at 270, and 360. So this is sine graph. This x is equal to x naught sine omega t. Now the velocity time is a cosine graph. You see that now? And the cosine graph has its maximum at the origin. Okay, so it goes like this: 0 at 90, negative minimum at 180, 0 at 270, and again maximum at 360. So this is how the velocity varies with this time t. So it's a cosine graph. All right, so this point here where we have the maximum, of course that's the maximum velocity. That gives us omega naught times x. That's the expression for our maximum velocity. And this point here on the displacement time graph is my amplitude x naught. So we expect that this, the amplitude of the velocity equation, velocity graph will be greater than the amplitude of the displacement time graph, because the amplitude is given by the product of the angular velocity multiplied by the displacement. Okay, this is supposed to be x naught. Okay, sorry, omega times x naught. All right, so for the acceleration, we have, you come back here now, my omega squared x naught becomes the maximum acceleration. I can write that as a is equal to minus a naught sine omega t. So where my a naught is the amplitude of this acceleration time graph. Okay, so that will also give you, being a negative, because you can see that this negative implies that this is going to be a naught multiplied by negative sine omega t. Okay, so that is like if you have a mirror image of the sine function, so this negative means you need a reflection of the sine graph along the time axis. Negative sine, a reflection, that will give you something like this, like this, like this, okay, and like this. So this is the acceleration time graph. So this point here is my maximum acceleration, which is omega times v naught. That's maximum acceleration, negative. And then here we can call it positive omega times v naught. Okay, so sometimes this could be called maximum acceleration, and this we call minimum acceleration. Minimum acceleration, that is to say theoretically, but in practice, we don't have negative acceleration. So negative acceleration is seen as deceleration or retardation, as the case will be. So this is how the three parameters, displacement, velocity, and acceleration vary with respect to time. Okay, another video we shall continue from there to look at the how to apply this principle to look at the period of some bodies in simple harmonic motion.